A soap dispenser appears unremarkable. It stands on a sink or counter, quietly waiting, a bottle filled with liquid, a narrow pump rising from the center, a curved nozzle pointing slightly downward. You press. Soap appears in your palm. You release. It resets. The simplicity hides a chain of problems that had to be solved before this form could exist. Before liquid soap dispensers became common, soap lived in bars. Solid soap had advantages. It required no container. It lasted long. It was inexpensive to produce and transport. But bars of soap were designed for private use in a time when bathrooms were less shared. As public restrooms expanded in the late 19th and early 20th centuries, bar soap revealed weaknesses. Shared bars accumulated residue. They became soft when wet and slippery in hands. They left rings in sinks. In high-traffic spaces, they degraded quickly. More importantly, concerns about hygiene grew. Even if scientific evidence about transmission via bar soap was debated, perception mattered. People did not like the idea of handling something dozens of strangers had touched. Liquid soap addressed perception first. A liquid stored in a closed container appears cleaner. It flows fresh each time. It avoids the visual wear of a bar. But introducing liquid created new constraints. Liquid must be contained. Early liquid soaps were stored in refillable containers or poured from bottles, but pouring created waste. The user had to estimate the amount needed. Too much flowed out. Too little required a second pour. Containers became sticky around the opening. Soap dripped down the sides. The problem was not soap, it was control. To control liquid, you need a valve. The modern soap dispenser's pump is a compact solution to fluid management. Inside that simple plastic head lies a small chamber, a spring, and two one-way valves. When you press down, the spring compresses. The chamber decreases in volume. Soap is forced upward through the nozzle. When you release, the spring pushes the pump back up. The chamber expands. A lower valve opens, drawing soap up from the bottle through a narrow dip tube. Meanwhile, the upper valve closes, preventing air from being pulled back through the nozzle. The aha moment often arrives when you realize the pump is not just pushing soap out. It is managing air. Air is the invisible adversary in liquid dispensing. If air enters the wrong place, the pump loses prime. It sputters, it drips, it fails to deliver consistent volume. The entire mechanism is designed to control not just liquid flow, but air exchange. The long, thin tube inside the bottle serves this exact purpose. It reaches the bottom, ensuring nearly all liquid can be accessed. Its narrow diameter regulates flow and reduces turbulence. If the tube were wide, the pump would require more force and deliver inconsistent amounts. The nozzle angle is another quiet decision. Why does the spout curve slightly downward rather than straight out? Because gravity assists closure. After the pump is pressed, a small amount of soap remains near the nozzle opening. If the spout pointed horizontally, soap would drip forward. If it pointed upward, residue could pool. The downward angle encourages excess soap to fall into the user's palm during dispensing and minimizes post-use drips. Drips matter more than aesthetics. In kitchens and bathrooms, soap residue accumulates quickly. A dispenser that drips creates sticky buildup. Sticky buildup attracts dust and bacteria. The design must prevent secondary mess. The spring inside the pump is tuned to a particular resistance. Too stiff, and users must press hard, making one-handed operation difficult. Too soft, and the pump may not return fully, allowing air infiltration or partial dispensing. Human behavior shapes that resistance. Most people press with varying force. Some press lightly, some press rapidly. The pump must deliver roughly the same amount regardless of pressure differences. This requires internal channel sizing and valve calibration. Then there is the bottle itself. Why tall and narrow rather than short and wide? Counter space is limited. A narrow footprint fits beside sinks without crowding. A taller shape allows gravity to assist liquid settling toward the dip tube. A wide bottle would be stable but consume more surface area. A very thin bottle would tip easily. The base diameter reflects stability calculations. The bottle must resist tipping when pressed from above. Each pump action applies downward and slightly forward force. The center of mass must remain within the base. Material choice matters too. Most soap dispensers are plastic. Plastic is lightweight, corrosion-resistant, inexpensive, and moldable into complex shapes. It allows for transparent windows showing soap levels. However, plastic threads and pump mechanisms can wear. Higher-end dispensers use metal or glass bodies, but the pump head remains plastic or stainless steel with internal plastic components. Metal springs resist corrosion but increase cost. Trade-offs emerge clearly here: durability versus affordability, weight versus portability, refillability versus disposability. In commercial settings, wall-mounted dispensers evolved further. These use larger reservoirs and sometimes sensor-based pumps to eliminate touch entirely. Motion sensors detect hands beneath the nozzle and trigger motorized pumping. Touchless dispensers respond to another layer of human behavior: avoidance of contact. But even these rely on the same core fluid logic: chamber, valve, controlled release. The consistency of soap viscosity also shapes the pump. Liquid soap is thicker than water. Its viscosity requires specific channel diameters. Too narrow and resistance increases. Too wide and uncontrolled flow occurs. Manufacturers design soaps to match pump performance and pumps to match soap viscosity. They evolve together. Why not use gravity alone with a simple spigot? Because gravity dispensing leads to leakage. A spigot left open or poorly sealed allows continuous dripping. It lacks metering precision. The pump, by contrast, meters a fixed volume per press. Metering is essential. Soap must be dispensed in small, repeatable quantities. Excess soap wastes product and frustrates users. Insufficient soap leads to double pumping, increasing wear and time. The pump head's size and surface texture also reflect ergonomics. It must be large enough to press comfortably with fingers or the heel of a hand. Some designs widen the top for easier operation by children or individuals with limited dexterity. The entire form emerges from repetition. A soap dispenser may be pressed dozens of times per day. In public settings, hundreds. It must endure constant vertical compression without cracking. Internal seals must maintain integrity through thousands of cycles. Even the threading that connects pump to bottle solves multiple problems. It must seal airtight to prevent leaks. It must allow easy removal for refilling. It must accommodate manufacturing tolerances across different bottle molds. The most important insight, though, is not mechanical. It is behavioral. Soap dispensers exist in shared spaces. Shared spaces amplify friction. Anything that creates mess, uncertainty, or contamination spreads quickly in perception and reality. The soap dispenser's shape reduces ambiguity. You see the nozzle. You place your hand beneath it. You press once. You receive a measured amount. No guessing. No touching shared surfaces beyond the pump itself. Over time, that predictability becomes invisible. When you encounter a poorly designed dispenser, one that drips, sputters, or requires multiple presses, you immediately notice. That contrast reveals how refined the standard design has become. Invisible design often hides in failure prevention. The soap dispenser is not impressive when it works. It is only noticeable when it doesn't. The curve of the spout, the spring tension, the dip tube length, the valve placement, none are decorative. They are solutions layered atop each other to prevent drips, airlocks, contamination, and waste. And here is the deeper realization. The soap dispenser is less about dispensing soap than about regulating behavior. It limits quantity. It shapes hand positioning. It encourages brief interaction. It maintains surface cleanliness. It supports hygiene rituals. Its form is not arbitrary. It is tuned to the physics of thick liquid and the unpredictability of human hands. What began as a response to concerns about shared bar soap evolved into a compact fluid control device sitting quietly beside sinks worldwide. It is one of the simplest visible objects in a bathroom and one of the most constrained. When you press down and feel the smooth resistance, you are compressing air, sealing valves, moving viscous fluid through narrow channels, and releasing exactly the amount engineers intended, all in a fraction of a second. Invisible design is not loud. It is the art of eliminating friction so thoroughly that you forget there was ever a problem to solve. The soap dispenser does not look engineered, but every millimeter of it is. And once you see that, it becomes difficult to look at it the same way again.